And no. Yes. Okay. Thank you. सोना सर या तो आप सेंटर में आइए या इधर आइए माइक के नजदीक नहीं इधर हाँ इधर ही आएंगे ये इधर ही आएंगे तो नहीं आप तो सिर्फ पीपीटी पे
So,
स्लाइड्स
sorry for the delay. Due to disturbance in electricity supply, we couldn't start in time. I apologize for that. Now we are starting the proceedings. At the very outset of this online lecture, I welcome you all who, who have joined online as well as offline. I thank you all for joining us. And since it has been quite delayed in starting this lecture, so without going into the formalities of this, all kind of formalities, may I directly request our Honorable Principal Professor O.P. Rai sir, Bareilly College, Bareilly, to give his welcome address so that we can start the proceedings.
Okay.
Our respective principal, Professor O.P. Rai sir.
Ji, thank you. Department of Physics, Bareilly College, Bareilly, and Indian Society of Physics Teacher. Collaboration. Both collaboration. Seminar, जो भी webinar, Semiconductor Optical Detector and Overview. All resource person for today's lecture, dear Dr. Sona Das, distinguished member of the Indian Association of Physics Teacher, faculty member from various departments, dear students, alumni of the Department of Physics, and all participants joining us through both online and offline modes. A very warm and cordial welcome to you all. It gives me immense pleasure to welcome each one of you to this online lecture on semiconductor optical detectors and overview organized by Department of Physics, Bareilly College, Bareilly, in collaboration with the Indian Association of Physics Teachers, Uttar Pradesh. I extend my heartfelt gratitude of our distinguished speakers, Dr. Sona Das from the Semiconductor Laboratory, Chandigarh, for graciously accepting our invitation despite his busy professional commitments. We are privileged to have with us a scientist of his eminence and expertise. His vast experience in semiconductor technology will enrich the knowledge of our students. The Department of Physics is consistently providing learning opportunity beyond the conventional classroom. I am delighted to see the ethnic participation of our postgraduate student and faculty members. Before I conclude, I once again express my sincere appreciation to the speaker for sharing his valuable time and expertise with us. I also congratulate the Department of Physics and IAPT RC-4 Uttar Pradesh for their continued efforts in promoting quality physics education and fostering scientific temperament among students and teachers alike. with these allies. With these words, I wish the program great success and a fruitful academic interaction for everyone. Thank you so much. Jai Hind, Jai Bharat. Thank you.
Thank you, sir, for your blessings. We will definitely work as per your advice. And since the time is already late, so let me briefly introduce the speaker for today's online lecture. Today's online lecture will be delivered by an eminent scientist from Semiconductor Research Laboratory, Chandigarh. He is Dr. Sona Das. He has obtained his Ph.D. degree from IIT Kanpur in the year 2018-19. And in the year 2019, he joined Semiconductor Laboratory, Chandigarh. And since then, he is working as scientist there. And he has expertise in several fields. His research interests include simulation, fabrication, and characterization of semiconductor optoelectronic devices for various strategic applications. With warm welcome, I now invite Dr. Sona Das to the platform to present his lecture and to guide our faculty and students with the today's topic that he has chosen semiconductor optical detectors and overview. So, Dr. Sona Das, the platform is yours. Now you can start, Dr. Sona Das.
Okay, thank you, Dr. Sundar and Bareilly College for giving me the opportunity to give a talk on this topic on that is actually semiconductor optical detectors and overview. Thank you for the introductions. Without delay, I'm just starting my presentation. So I'm sharing my screen. So is it visible to you? Hello? Hello, Professor Sundar?
It is not visible.
Is it visible now?
Hello.
Hello?
Not visible.
Is it visible?
Your slides are not visible. You are visible. Are you sharing your slides?
Yeah, I'm sharing. Just a minute.
Oh, okay. So you are visible to us as well as audible. Sir.
Is it the slides are not visible? Just tell us. I'm online. Or they are visible, please see.
Is it visible now, Professor Sundar?
Yeah, I still think we make it full screen.
Hello?
Yeah, you see, you keep still sharing yours, sharing.
नेटवर्क का प्रॉब्लम था आप ना इसको शेयरिंग मोड में वो ना करो फुल स्क्रीन में
अच्छा, okay.
छोटा स्क्रीन पर अब जी
Professor Sundar, the slides are visible from your side?
No, slides are not still visible.
Just a minute.
is
It
there
is showing you are screen sharing.
okay
Just a minute, we're trying.
just a minute the person
Sharing नहीं हो रहा है, मैं तो share
sharing
Now it is visible, Professor Sundar? The slides are visible from your side?
No, sir, it's still not visible. It is showing a message you are screen sharing. Green
just
message.
hold up the person is 80% is trying
Now it is visible?
Yes, yes. Now it is visible. You may start,
So,
please.
make it full screen. So, yeah.
Just
Now it is visible now?
Full screen is
Full screen is visible?
Yes, yes.
Yes, you can make it slideshow mode.
Okay, so anytime you can stop me if it is not visible or if you have any questions on this.
I will
So
let you know.
without delay, I'm just starting. So my title of my presentation is Semiconductor Optical Detectors and Overview. So what we do at SCL? So basically, SCL is a one-stop solution starting from, let's say, design, process, design, the fabrication, assembly, testing, packaging of different kind of devices like CMOS, VLSI devices, various kind of processors, memory devices, like different kind of optical imagers like CCDs, CMOS image sensors. Presently, we have started different kind of sensors we design, fabricated, and tested. Like accelerometer, gyroscope, and different kind of pressure sensors. And then we characterize these devices and we package on a dedicated package and we test it and we deliver to different kind of users and as a kind of space qualified devices we deliver to the various kind of strategic applications. So at SCL, basically we have two different type of fabrication lines. One we call at 18 fabrication process lines. So I am audible, no, Professor Sundar?
Yes, sir.
Yes, sir, you are.
You are audible.
Okay.
Yes, you are audible. You just make your slides in the slideshow mode.
So this is the full screen I have already shared.
Okay, sir. Okay, sir. You may continue.
Okay. So basically the 8-inch fabrication lines, so it actually handle 8-inch diameter of silicon wafer, where the technology node we use 180 nanometer. So 180 nanometer basically a gate length of the MOSFET, so that we call it 180 nanometer. So minimum features that we can print on this line is 180 nanometer minimum feature size. And here we target different kind of CMOS devices. And for the imagers, optical devices like CCDs, we newly started the CMOS image sensors development in this fabrication line. So we have another fabrication line that is a 6-inch line where we can handle the 6-inch diameter of silicon wafer. And the minimum feature size we print in this line is 0.8 micron. Okay, so it is a little bit larger as compared to the 8-inch fabrication line. So, and this line actually used for different kind of MEMS devices and different kind of charge particle detectors. Okay, and some kind of optical detectors we fabricate in this 6-inch line. Coming to the next slide, basically we deliver so many devices to ISRO. Like as you know that this is one of the very important devices we actually deliver to ISRO for call it Vikram 32-bit processor and Kalpana processors, and they basically use for the navigations, control, guidance of the spacecraft and the satellites. And apart from the CMOS, mainly I mainly involved in development of various kind of silicon detectors like CCDs. So we have various types of CCD imagers, mainly used for various kind of remote sensing applications. For the remote sensing applications, mainly linear imager is used, and so you can see there in the slides there is a 4K linear imager, means it has 4,000 pixels. Okay, on the silicons, 4,000 pixels in one row. So, and each pixel size is 7 micron cross 7 microns square pixels. And as it is a silicon material, so it can cover the wavelength range from 520 nanometer to the 860 nanometer. As you know, the silicon is capable of detecting the wavelength from 400 nanometer to the up to 1050 nanometer. And this we deliver from one of the missions called YIMS-1. So another in the right side, if you see, there's another imager is called 48 cross 4000 frame transfer CCD. So this we developed for one of the missions, Oceanoset 3. This is basically that used for to study the ecosystem of the ocean. and various kind of agriculture application and the various pollution monitoring applications. So this is actually 48. It has 48 rows, and in one row there is a 4,000 pixels. This is a linear array. And
Dr. Das, let me interrupt you, please. Your slides are not moving. Only first slide is there.
Okay, it's the second slide is not moving.
You are just on the first slide right now.
No. I am just moving to the second slide.
Second slide. Okay. All right.
No, now it is visible. Hello.
Yes, it is visible now.
No, if I make it full screen, now it is visible.
Yes, sir, visible.
Now I'm changing to the third. Is it visible now? Third, fourth
Third
slide.
slide. ISRO slide is visible now. ISRO.
Fifth one. Okay. So actually, if I make it full screen, no, so it is not visible. Okay, so I am not making it full screen. So now I'm in the second slide. So I'm introducing the different kind of linear images that we developed at SEAL. So if you see the top right is a frame transfer CCD. Okay, so so this is actually a photogate based imager. So I'll introduce all this photogate. What is photogate? What is photodiode? Basically, these are the building blocks or the basic photosite element in the CCDs. And there is another linear images called 12K. It's a very large linear detector. So it has 12,000 pixels in a row. So so basically the linear imager are mainly used for the remote sensing applications. And there is in the this is the detector, so 1K by 1K frame transfer CCD. This is a area imager. Is a basically 2D imager. Earlier one is a 1D linear imager. So this 2D imager is for the star sensor sensing application, basically to precisely determine the orientation of the spacecraft or the satellite in the space with reference to position of any kind of known position of the stars in by actually viewing the known catalog of the stars in the space, so we can precisely determine the position of our space satellite or the spacecraft in the space. So actually the area image is mainly used for the that purpose to determine the precise location or orientations of the spacecraft. So this is a so we actually develop various kind of semiconductor detectors. We develop CMOS image CCD image sensors. Okay, both linear and area image sensors. We newly started the development of CMOS image sensors, and we develop various kind of silicon PIN detectors, various kind of silicon charge particle detectors, silicon phototransistors. Newly, we have started developing the compound semiconductor-based IR detectors and other solar cells type of devices based on the compound semiconductor for space applications. So mainly, who are the users for our devices, like ISRO and other various kind of strategic organizations, and we develop various kind of detectors, charge particle detector for CERN, for various kind of high energy physics experiments, which have been carried out at CERN. Okay, so moving to the next slide. Full screen is visible. Hello? Hello?
It is not full screen, but something is there.
This title of the slide is optical detector space application. Is this visible from your side?
Yes, visible.
Okay. So mainly we as I have shown here, this is the one kind of linear imager that was used for the ocean monitoring applications. This is actually launched in 2022, and the mission was Oceanoset 3 mission. Basically, this is a it is a combination of 13 bands of 13 bands, or means 13 detectors starting from 400 nanometer to 1000 nanometer, and each band has different applications. We mainly assemble these devices in the satellite, and then all the payloads have been assembled in Space Application Center, Ahmedabad, and it was basically launched in LEO orbit, low Earth orbit, for various kind of remote sensing application. This is a composite image of all the 13 bands. Okay, so this detector is called the OCM detector, Ocean Color Monitor Detectors. Okay. So how this imaging is done using this linear imager? So coming to the slide number 8, the title of the coming slide number, next slide I'm coming, the slide number 8. So actually this imaging is done with the linear imager. So basically this is basically a method is called the push broom scanning method. In the push broom scanning method, the linear imager or the linear detector array is actually perpendicular to the scanning directions, and at a particular frame time, it actually captures a 1D line of image. Okay, and when the satellite moves, this covers another line of the having a different swath area in the on the ground, and so each scan it actually covers a 1D scan or the 1D image, and when to get the complete 2D image of the ground is basically the signal is a signal processing method like stitching of the 1D images. It actually does, and it will actually generate the complete 2D image of the ground. So basically this way the linear imager used for the remote sensing applications. Coming to the next slide. So what is the basic principle for these detections? As you all know that electromagnetic spectrum actually covers a wide range of wavelengths starting from, let's say, gamma ray to X-rays, UV, visible, infrared, microwaves, and radio waves. Okay, so mainly we are concentrating in this lecture on the visible to infrared range. Okay, so visible range is starting from, let's say, 380 nanometer to 750 nanometer in the visible range, and above 750 nanometer is near infrared, and up to 2 micron is called the shortwave IR detail range, and the long IR range is covers from 3 to let's say 14 micron wavelength. Okay, so what is the basic principle for this remote sensing applications? Basically, there are two mechanisms. Either the light is actually basically anyway the light should be fall on the detectors. Okay, the light can be coming by the reflections of from any objects, okay, and then directed to the detectors. So in that case, if it is a visible range, so the source is the sun. So in that case, the light is coming from the sun, it's reflected from the object and is going to and directed to the detectors, and we can see the objects. Okay, so this is basically a kind of active imaging. And another imaging method is called the passive imaging, where there is a passive imaging, means the light is emitted by the object itself. Okay, because as you know, any object above 0 Kelvin, it exceeds the infrared range and peak wavelength at around 10 microns. Okay, and by sensing this imaging emitted light, we can sense or we can image the objects. Okay, so these are the basically two mechanisms for this kind of detection principle, and you know that the different objects actually emit or reflect different part of the electromagnetic spectrum. Like you can say, and to detect the vegetations or the chlorophyll content, means I am talking about the remote sensing application part. Let's say one of the applications is the chlorophyll content in the vegetations, or chlorophyll content in the leaves or the crops. Okay, so as you know, in the summertime it has a high content of the chlorophyll, and chlorophyll actually reflect the green part of the electromagnetic spectrum in the visible range, but it absorbs the red part of the visible range. So by detecting the differential intensity of these or two different detectors, like there is a one linear imager which is covering on the red light, and another linear imager actually mainly detection for the green light, by using some different kind of filters on the window of the imager. So I can, if I make a differentiations between the two. Hello. 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 Hello, Professor Sundar. Professor Sundar. Are you audible?
Yes, you are audible.
Yes, sir, you are audible.
Yes, sir. Yes, sir. You are audible.
वेस्ट, नॉर्थ, साउथ, ईस्ट, वेस्ट, सेंट्रल, पांचों रीजन से 25-25 बच्चे कॉल करते हैं, टॉप 25, और उनका कैंप करते हैं। तो ये मैं इंफॉर्मेशन देना चाह रहा था, यदि आप चाहें तो इसको कर सकते हैं आप। ओके, ठीक है सर, ओके, बाय।
हेलो।
यस।
Hello.
Yes, sir, you are audible.
Okay, so linear imager mainly used for various kind of remote sensing application like vegetation health monitoring, chlorophyll concentrations, and different kind of crop health monitoring, and different kind of environmental monitor like aerosol concentration present on the atmosphere that we can monitor using this kind of linear imagers, and various kind of oceanography application, as I already mentioned, for the OCM detector. And apart from this remote sensing, these detectors have been used for various kind of industrial, medical, and military applications. Okay. So coming to the next slide. So what is the heart of these detectors? Basically, this is a silicon, and as you know that how this silicon is formed, the crystals. Actually, basically, as you know that the silicon has 14 electrons, and in the outermost shell it has 4 electrons. So it forms a covalent bond to the nearest neighbors of the 4 silicon atoms, and it forms a stable the crystals. So how the silicon actually detects the light? Basically, as you know that to detect the light for any material, the band gap should be smaller than that energy of the photon. It means if the energy of the photon is equal or greater than the band gap of the material, so it will absorb the light. Okay. So and there is a very very simple relation is there from the E is equal H nu, that if we calculate, so we find out that lambda in micron is 1.24 divided by band gap of that material in EV. So if it is the band gap of the silicon, so it is 1.12 EV. So you can see that calculated, it's a lambda in micron is around 1.1 micron. Means up to 1.1 micron it will detect, and above 1.1 micron it will transmit the light. Okay, because for energy of the photon is now less than the band gap of the silicon, so it will transmit. Okay, so you can also see in this chart that gallium arsenide band gap is 1.42. So it has a cutoff wavelength lower than the silicon. And if you see the germanium band gap is 0.72 EV. So it has actually a higher cutoff wavelength as compared to the silicon. Okay. Okay. Now you can also see that absorption coefficient is basically a wavelength dependent. And you can see that higher the wavelength, absorption coefficient is lower. So in that case, to get a similar amount of absorption of light, I need a higher thickness for the higher range as compared to the in the near infrared range as compared to the lower part of the visible range. It means if you see the absorption coefficient and the absorption depth are actually inversely related. So absorption depth, you can see the to absorb. So so basically, what is absorption depth? Absorption depth basically the depth at which the intensity of the light. Hello.
Yes, sir, you are audible. Please continue.
Some voices coming from your end. Some voices are coming.
Yeah. सभी लोग म्यूट कर लें अपने आप को. Please.
All the participants are requested to please mute yourself.
Okay. So one more thing, if I changing my slide, is it visible from your side? Let's say I'm changing now. Is it visible?
Yes, sir.
Is it visible now? The changing slides are visible?
No, sir.
It is showing slide number 10.
Okay, slide number 10. Okay, so now that means if I make it full screen, there is not. Okay. Okay, so here actually the absorption depth is basically the depth at which the light is absorbed 70% or 60, basically 60, 70, around 70% of the incident light. So if you see for the silicon, okay, so to absorb let's say 1100 nanometer, I need around 100 micron of thickness, okay, and I needed let's say 70% of the light to absorb for the wavelength of 600 nanometer, 500 nanometer. I need a 1 micron thickness. So that's why means this because of this absorption coefficient variations with the wavelength means if I let's say on a single silicon substrate, if I want to make a different kind of detectors like one linear imager is detect the let's say 400 nanometer band, another linear imager detector let's say 600 nanometer band, another detector let's say develop for the near infrared range. So I have to see because I have to design the thickness accordingly, because you can see the blue part of the light is absorbed very thin within the very thinner portion of the silicon, and if you see the near infrared range, it needs a thicker portion in the thicker silicon layer. So accordingly, I have to design the thicknesses of the silicon for the different bands of the light. Okay, so this is basically for the designer purpose, the designer actually point of view how they will design for the different detectors on silicon. So why silicon? Basically, silicon is used for the detectors. Silicon is basically mature technology, and we can integrate both the detectors with their readout circuits. Okay, and high integration density, because you can use the same CMOS foundry for this for development of these detectors, and silicon has high absorption coefficient starting from visible to near infrared range. So that's why silicon is very popular in the visible to near infrared band. Okay, so and now coming to the imager or imaging that working principle. Okay, so what are the basic functions of a CCD imager? Coming to the slide number 11. Okay, so basically there are four basically basic principles or basic operations. One is charge generations, basically to generate the electron hole pairs. So from the incoming light, so I have to I have to design my detectors accordingly, and the generation of electron hole pairs is by internal photoelectric effect. And there is the next process, the charge collections. After generating the electron hole pair, I have to collect the charge in a kind of potential well. Potential well, and then I have to transfer the charges to some dedicated location. We call it sense node or dedicated detection node. So accordingly, we have to design the patterns or the voltage clocks on the CCD so that I can transfer the charges to the dedicated locations, and then charge detection, because the only electron hole pair generations cannot give you the physical parameters like then I have to convert that any charge to either voltage or current. That actually purpose is a last working principle like charge detection. Okay, so basically coming to the next slide. Basically, CCD has two different kind of photosite element. One is called the photodiode based. What is a photodiode? Photodiode basically simply junction junction diode is a PN junction diode, and it has some opening to absorb the light. Okay, so as you know, this is basically a PN diode, and when you sandwich the PN N-type material, it forms some kind of depletion layer. Okay, and this is a typical charge distribution in the depletion layer, or this is called the space charge layer. So it has in the N side, vicinity of the N side, there is a positive charge, and vicinity of the P side, there is a negative charge. And if I integrate, as you know from the Gauss's law, del dot E is equal to rho by epsilon. If I integrate my charge, I'll get the electric field. So these are basically the electric field profile in the junction or the depletion layer. And from the relation from E is equal to minus dE by dx. So basically, if I integrate my electric field, I will get a potential profile like this. Okay, so as you know, and from relation and from how the potential and energy is related, from E is equal to Q into V. Q is the charge, which is the negatively charged particle like electrons. So E is equal to Q into V means the higher the potential, lower is the energy. Means if I generate any kind of electron hole pair, my tendency of the electron to move in the higher potential or in the lower energy side. Okay, so this is basically a PN junction formed by ion implantations, because basically this is we start with a p-type material, then we implanted p-type material, then we implanted n-type material using either phosphorus or arsenic. And if you see, there is a electric field, built-in electric field formed between this N and P, and there is a depletion layer formed between these N and P junctions, and electric field direction from N to P. Okay, when the light shines from the top, then electron hole pair generated in the depletion layer. Okay, so because I already mentioned, the electron's tendency is always moving to the higher potential side. So because field is from N to P, or N is means positive, P is basically negative. So electrons has negative charge, it will move to the N side, and holes is moving to the P side. Okay, so and as a result of which I'll get some current, because any movement of the charge gives you the current. Okay, so basically this is a basically IV characteristics of any kind of junction diode. So if you see, this is a reverse bias and this is a forward bias. Detectors mainly operate in the reverse way, because I have to deplete all the kind of free carriers found in the depletion region, and any kind of electron hole pair formed in the depletion region, so it will not recombine. So that's why I have to deplete the charges from the active volume of the detectors, so that I'll get a adequate or the sufficient amount of current through this device. So there should not be any kind of losses because of the recombinations. Okay, so basically the main point is that I have to operate my detectors in the reverse bias conditions, means negatively biased. Okay, so if I increase the intensity of the light, according to my current in the reverse current is increased linearly. Okay, and I have to also ensure that my operating regions should be in the linear regions of the detector. Okay, so coming to the next slide. Okay, so previously it was a photodiode type of basic building block of the photosite element. There is another photosite element is called the photogate or MOS capacitor based. Basically, in the MOS capacitor, there is a metal, or basically we use a polysilicon gate, and there is a oxide, and there is a p-type silicon. Okay, so when we apply a positive bias, again in the same way as PN diode, I can deplete the charges. Okay, I can make a depletion layer in the silicon by using any voltage apply, positive voltage apply on the gate. Okay, so my electric field profile will be like this. Okay, and after the depletion, electric field is almost negligible. And any kind of, and this is a potential profile. By I integrate the electric field, I'll get a potential profile. Any kind of electron hole pair formed in this layer, it is actually moving to the higher potential side, as I already mentioned. So it will collect in the silicon. So basically, this is a part that we call the charge generation. As I mentioned, there is a four basic methodology to be followed. one is charge generation. That is called the charge generation. Now, because of the potential wave form, I can collect the charges. Okay, these charges are collected in the locally in this under the gate. Okay, now third process is the charge transfer. But this is a kind of pixel regions. So where I have to use different kind of phases or different kind of photo gate or different kind of MOS capacitors in the single pixels, so that by appropriate voltage applying on the different phases, I can move the charge from one location to the another locations. That means the third step is called the charge transfer to the dedicated locations. So, okay, so like that way, I have to transfer the charges from one location to another location by using some kind of appropriate voltage programming on the detector. Basically, there should not be any gap between the two photo gates. Otherwise, there will be a potential spike. So, if you see in the right side, we mainly use the two polysilicon gates, and we fabricate such that there should not be in the gap, and there is a oxide. The separation between the poly 1 and poly 2 means one gate to another gate. There's some kind of isolation be using the poly gate. So, and you can see there is an overlap between the poly 1 or poly 2. So there should not be any gap in the transfer directions. Okay. So this is the second photosite element that I have discussed earlier. Earlier one is photo gate. Now this is a photodiode. This is a photo gate. Coming to the next slide. So as you know, as I already discussed, that actually the charge we have to the higher charge is going to the electrons are going to the higher potential side, and it is collected in the silicon surface. And as you know, the silicon surface has various kind of the surface states, so it will lead to various kind of recombinations and gives you the higher leakage current, because the detector, the main parameter is the leakage current, that we have to reduce as much as possible. So to reduce the leakage current, there is another the architecture is called the Bareilly channel MOS structures. Means we have to implant a separate N channel beneath the gate oxide. So there is a basically earlier the N channel was not there, so it's called the surface channel. Now we call it a Bareilly channel. So there is a N channel in between the gate oxide and the substrate. So in that case, there is basically two junctions. One is the junction coming from the top side. If I apply any kind of positive bias, it will actually deplete in the N channel. This N channel will deplete. And if I apply the bias from this PN junction is formed, so there another junction is coming from the back side. So when there is a meet, both the depletion regions actually will meet, we'll call it a punch through. Then the maximum potential will fix at a particular location point, which is actually below the surface of the silicon. So in that way, you can see the maximum potential is not at the surface. Maximum potential is now located at the beneath, is actually beneath the gate oxide. So it actually is buried inside the semiconductor, so that when any kind of electron hole pair formed in these junctions, so electrons will collect at the higher potential. So now it will flow through that location. So electrons will not face any kind of surface state. So accordingly, the leakage current will be very low. So coming to the next slide. Hello.
Yes, sir. You are audible. You may continue,
Okay.
please.
Okay. So coming to the working principle of the linear CCD imagers. Linear CCDs actually is basically use a photodiodes. As I already mentioned, basically linear CCD and area CCD, either they can, so linear CCD mainly use a photodiode or photogate, but area CCD is always use the photogate based or MOS capacitor. Okay. So this is the linear CCD. So this is a photodiode. I have to reverse bias. I have to use a reverse bias on the photodiode. So I use a storage charge. Storage gate. I use a storage gate to bias the photodiode. So I basically, when the light shines on the photodiode, I will collect the charge. So this is I will generate the charge. I will collect the charge in the photodiode. Okay. Now I have to transfer the charge. The third actually the state. I have to transfer the charge. So there is a kind of transfer gate. When I apply higher bias to the transfer gate, my charges located at the photodiode region will now transfer to the higher potential side in the transfer gate. and then I have to collect the charges in the horizontal shift registers. There is called a horizontal shift registers. So apart from these photodiodes, all are metal shielded. So there should not be any carrier generations in this kind of storage gate, transfer gate, and the horizontal shift register. So these are all shielded by the metal. Okay. Now after collecting the charge in the horizontal shift registers, now again the horizontal shift register has different phases or a different. This is basically another MOS that capacitor based the transfer. So after collecting here the charge in the horizontal shift registers, I have to move the transfer charges to the detection node. So I have to transfer the charges, like I have to apply higher potential in the next phase. So transfer the charges from here to the next phase, and again I have to transfer the charges from here to here. Accordingly, I have to program that voltage pulses accordingly, so that I can transfer the charges. Ultimately I have to transfer charge to a sensing node, where there is a capacitor. Is basically a junction capacitor is present at the sensing node, where this charge to voltage conversion takes place. Anyway, I have to convert the charge to the voltage, the physical measurable parameters. So I have to convert the charges to the voltage, and then finally, basically these are all, and I have to amplify the voltage. Basically, these are analog output, and further I have to use the analog to digital conversion to get the digital output. Okay, so this is the basic operation of the CCD linear imager. Okay, and now I'm coming to the next slide. So where I'm coming to the area imager. What is the working principle for the area imager? So in the area imager, I have to use a photo gate based or MOS capacitor based photo site, where each pixel is basically covered by either 3 or 4 phases. Phases means, in this case I am mentioning here, these phases means one phase means this is one MOS capacitor, another phase means another MOS capacitor. Like this way, I can use either I can use a 3 phase or I can use the 4 phase. Okay, and accordingly I have to pattern my clocks so that I can transfer the charges from one location to another location. Okay, so let's say all the pixels, like say this is a red covered, this is one pixel, this is another pixel, this is another pixel, like that. There's a rows or pixels. Okay, there's a area images. Now all the pixels are simultaneously they generate the charges. Now I have to transfer the charges to this sensing node. How I will do that? I have to use a vertical shift registers, where I have to transfer the charges vertically from this location to ultimately this location, and in the same way I have to use a horizontal shift registers. So I'm just making one animations like this way. So let's say this is my charge I have collected here. Now I have to transfer the charges to here. Now transfer the charges to here. Means I am transfer the charges from, let's say, first row of pixels to the last row of pixels. And ultimately I have to transfer the charges to the horizontal shift registers. Now the horizontal shift registers, I have to use a different kind of pattern generator or the pattern clocks, so that I can transfer the charges in the horizontal shift registers. So I transfer the charges in the horizontal shift registers, and finally I have to coming to the last phase of my horizontal shift registers, where you can see the horizontal shift register in the last phase has the higher potential. So I have to collect the charges in this phase. Okay, my electrons are collected here. Okay, and this is my sense node. You can sense node is basically N plus P a photodiode. Basically N plus P photodiode itself is a capacitor. Okay, now what I will do in the next slide I'm showing you. Okay, so next slide I'm coming here. So you can see here what I'll do here in the last phase. I'm just collecting the charges. Okay, at this time what I'll do, I use the monolithic transistors. One is called the reset transistor, and there is the source follower buffer amplifier. By applying a high to the reset transistor, I am making my capacitor to be charged. Okay, charged to this VDD value, the high voltage value. So my capacitor is charged now. It will give you this, and this capacitor, the source, capacitor output of the capacitor is connected to the gate of the source follower of the buffer amplifier. So now the buffer amplifier is actually giving the output voltage. Okay, now if you see in the clock, now how I'll design the clock. Now you can see this is my phase 3 of the last phase of my horizontal shift registers. So when it is high, my electrons are collected here. Now, when I switch on my the reset transistors, my actually output of the buffer amplifier output will be giving the high value because my capacitor is charged to this VDD value. Okay, now it's settled to a reference value. Now, when I make it low, of the phase, so now I can say phase T is now low. At this time, what will happen? Now the charges are moving to the higher potential, means because the capacitor is the higher potential, my charges are moving to the sense node. Accordingly, my sense node potential will be decreasing exponential. So this is not a sharp decrease, this is very exponential decrease. Basically, I'm discharging my capacitor. So accordingly, the difference between this reference voltage and my that signal value, I can give you effective value of my output signal. So if this is my output, this is my output voltage of my CCD. Okay, so if I get this output voltage, several important figure of merits I can determine of this CCDs, like linearity. Linearity means up to how much light intensity my CCD is giving the linear output, electrical output. And then charge to voltage conversion factor means how much charge I'm what is the efficient what is the how much voltage I'm getting out of a single electrons. Okay, and then full well capacity, that how much electrons I can collect in a particular the pixel or particular well. And then the CTA, how much efficient my transfer process is. And then modulation transfer function, how good my isolations or the between the pixels in terms of electrical and optical crosstalk point of view. Okay, and then finally the quantum efficiency means out of how many photons I am converting I'm getting the output electrons or in terms of voltage or current. So in this way, actually, we are mainly that characterize our the CCDs. Okay, so basically, what are the advantage of the CCD imager? Basically, CCD imager very high, it gives a very high resolution imaging, high sensitivity. Okay, high dynamic range. Dynamic range basically the maximum maximum intensity to the maximum detection intensity to the actually the noise level or the minimum intensity detections level. And then the high quality image we can get from using the CCDs, because the fill factor is 100% in the CCD, because there should not be any in the wastage area in the silicon pixels. And then high quantum efficiency in the near infrared, visible to the near infrared range. But what is the disadvantage? Disadvantage mainly basically low frame rate, because anyway I have to transfer the charges from the first pixel to the sense node. So I need a lot of time, or the frame rate is very low to transfer the charges from the first row of the pixels to the last sense node data positions. So it is a very low frame rate, and the maximum power consumption, because this each phase needs a very high voltage, like is more than 10 volt to 10 to 15 volt is needed. So its power consumption is more in this case of CCDs. Okay, but high end is a disadvantage is a higher manufacturing cost, because anyway all the readout circuits like for digital conversions I have to use it off chip, because normally in the CCDs we normally don't do any kind of on chip integrations of the any kind of analog digital conversions. Although nowadays this on chip this integrations of this ADCs are there in the CCDs. So these are the basically advantages and disadvantages of the CCDs. Okay, this is basically a typical CCD image sensor. This is a ACN image of the CCDs. This is basically all the image regions or the pixel regions. Okay, these are as I mentioned, these are vertical phase registered BSR pixels faces. So where I have to transfer the charge using these faces or the patterning of the clocks, I have to transfer the charges starting from here to the coming to the horizontal shift ratio. This is the HSR phases. Okay, and ultimately using the HSR clocks, I have to transfer the charges to the sense node. So you can see this is the blue encircled region is just basically sense node. Okay, so and the sense node is this is a sense node source, yeah, for this reset transistors. Okay, and this is the output buffer amplifier. Okay. Okay. So coming to the next topic, there is a. So is it visible, Professor Sundar? Professor Sundar?
It is visible.
Okay.
Hello. Yes, sir, you are audible.
Okay. So the next topic is slide number 31. This is the CMOS image sensors. Basically, the CMOS image sensors, actually the main advantage is that so we integrate, because earlier I mentioned that in the CCDs that sense node and all the buffer amplifier is common for all the pixels. We share the output amplifier and the output part of the circuit for all the pixels. But so, and that's why that the transfer frame rate is low. Okay, and in the CMOS image sensors, basically we all the pixels having their own readout circuit, means all the reset transistors and the source forward buffer amplifier are actually dedicated, is actually used for its own pixels. And means if I say this is one pixels, this is a pixel region, and all the readout circuits are actually integrated in the pixel itself. Okay, so that's why its fill factor is less, because no, in the and a portion of the pixels is mainly covered by the readout part of the circuit. So its actual fill factor is low. Okay, but the frame rate is very high as compared to the CCDs. Okay, because now no need to transfer the charges from one part of the pixels to the sense node, because now the once the carriers are generated in the pixel, it will collect it at the same instant. Okay, as a same issue. That's why the frame rate is very high. The main and what I'll do is basically I have to, if I select the rows, then I transfer this select rows, then I measure the output voltage of any of the pixels, and then accordingly I have to convert the analog voltage to the digital conversions I can take place in the pixel in the imager itself. So basically integration is possible in CMOS image sensor. So what is the advantage? As I mentioned, this is a high frame rate. Integration is possible for the, and miniaturization is possible because of the high integration. The CMOS process can be used for the CMOS image sensors, and low power consumption because the voltage operation is very low, 3.3 to 5 volt. Earlier the CCD, as I mentioned, this we use at 10 to 15 volt. So power consumption is low in the CMOS image sensors, and the lower cost because all the integration can be possible. So a readout circuit and everything is possible in the single monolithic substrate. So as a result of which the cost is low. But what is the disadvantage? As I mentioned, that resolution is poor because the fill factor is not high as compared to CCDs, because fill factor is low, and that's why it's a lower sensitivity. And it has actually because each pixel has its own amplifier, so it has some gain mismatch is there. So there is a kind of fixed pattern noise is also higher in the case of CMOS image sensors as compared to the CCDs. And it has also the quantum efficiency also for in the near infrared area, because my applied voltage is low, so I cannot deplete my silicon in the deeper and in the bulk in the silicon. So up till now, I'm talking about the silicon detectors, and the silicon detector is responsible up to the, as I mentioned, that up to the 1.1 micron silicon is useful, and above 1.1 micron is actually basically silicon is transparent. So for the near infrared light and the short wave infrared light, long wave infrared light, I cannot use silicon. From these simple expressions, if I put, so cutoff wavelength is 1.1 micron. So for that, I have to use a compound semiconductor, because silicon is elementary silicon semiconductors. Now for detecting the infrared range, infrared part of the electromagnetic spectrum, I have to use a compound semiconductor. Although silicon used as a bolometer, but it has some different limitations, like the sensitivity is low as compared to the compound semiconductors. Okay, so mainly high sensitive and high performance IR detectors mainly use compound semiconductor materials. Okay, so what is compound semiconductors? Compound semiconductor basically a combinations of group 3 and group 5 elements. Basically, by combining the two elements, I can make it a binary compounds like gallium arsenide. You can see gallium in the group 3 and arsenic in the 5. So I can make it gallium arsenide. I can make it indium phosphide. I can make it indium phosphide compound semiconductors. I can make it gallium antimonide, and means apart from the binary compounds, I can also make a ternary compound. Means 2 group 3 and 1 group 5, like indium gallium arsenide I can make. So I have a zoo of materials in the compound semiconductor family. So there is a huge flexibility to choosing the material, and which I can also, by choosing the material and the compositions of different elements, I can cover a wide range of the that operating wavelength. Like you can see, let's say there is a gallium arsenide. So gallium arsenide substrate is commercially available. So if I make it you can grow, let's say a composition of aluminium gallium arsenide. Okay, so ternary compound, if I grow on gallium arsenide substrate, I can make a ternary compound like aluminium gallium arsenide. Now you can see I can tune the wavelength from gallium arsenide to aluminium arsenide. Okay, in between this range I can cover, I can detect. Okay, similarly, if you see the indium phosphide, so indium phosphide substrate is commercially available. Like you can see, if I make a ternary like indium gallium arsenide, I like a small amount of indium, if I incorporate in the gallium arsenide, I can make it ternary like indium gallium arsenide, and it should be lattice matched to indium phosphide for proper to defect-free growth. Okay, now you can see by choosing the different compositions of indium, I can cover different part of the wavelength. To cover the wavelength, let's say from 1.1 micron to 2 micron, so I can use a indium gallium arsenide material on indium phosphide substrate. Okay, so like that way I can use different combinations of the compound semiconductor like ternary, even quaternary also possible on the compound semiconductor substrate to make different kind of near infrared and short wave infrared and long wave infrared detectors. So what is the difference between the silicon and the gallium arsenide? One basic difference is that silicon is a indirect bandgap semiconductor, so that, and for that silicon is not a good emitter. Like LEDs cannot be possible using silicon because there is a momentum, the mismatch is there. So efficient light cannot be taking out from the silicon. Okay, but gallium arsenide, if you say that is a direct bandgap semiconductors, means the direct bandgap means is the maximum of the conduction band and the minimum of the maximum of the valence band and minimum of the conduction band in the same place in K. So delta K, basically there should not be any momentum mismatch. Okay, so that's why the light emission is very efficient in the compound semiconductors like gallium arsenide, indium phosphide. That's why you can see various kind of most of the LEDs and lasers are coming out from the compound semiconductor like indium phosphide, gallium arsenide, gallium nitride. All the blue LEDs, white LEDs coming from are all from gallium nitride. All the red LEDs are from the gallium arsenide material. Okay, or any kind of near infrared detectors, LEDs are from the indium gallium arsenide or indium gallium arsenide phosphide materials. Okay, so all are from the compound semiconductors. What are the electrical point of view? It is mobility point of view. You can see silicon has electron mobility is 1400 centimeter square per volt centimeter second. But if you see the gallium arsenide is 8,500, is 6 times higher as compared to silicon. So any kind of high electron mobility transistors means for the various kind of high speed communications, we for that high speed communications we have to have use a compound semiconductors, detectors, or any kind of modulators. So for that I have to use a gallium arsenide or compound semiconductor materials, either gallium arsenide or indium phosphide. From the cost point of view, you can see for the 6-inch wafer, so silicon cost is around roughly around 10,000 rupees, and for the gallium arsenide, the same 6-inch surface is 50,000, and for the indium phosphide is 2.5 lakhs. So you can see the cost point of view, the silicon is very cheaper. That's why silicon is very popular, and now for the visible to near infrared range, even for the bolometer for the IR range also, silicon is very popular. But as I already mentioned, is very low sensitive and very low speed detector coming out of silicon using as a bolometer in the higher range. But most of the high speed detectors, high sensitive detectors in the higher range is basically from the compound semiconductors. Okay. So coming to the next slide. So basically now we have covered the silicon part of the visible part of the electromagnetic spectrum. Now coming to the near infrared and short wave part of the electromagnetic spectrum, which is covered from let's say 0.75 micron to up to 2 micron. So that means I'm covering near infrared to short wave detectors. So what are the materials is used to detect these materials? That actually use compound semiconductors. That I'm coming to the next. So why this range is important? This near infrared to short wave, because as you know, as you see, that visible light is very very scattering, and the absorption point of view is very high in the atmosphere or in the like fog or in the dust. As visible is very absorption is high in the this kind of pollutants. But if we compare to the visible light, short wave light, you can see this is quite transparent, because as you know that scattering is more in the lower wavelength as compared to the higher wavelength. So the higher wavelength is quite transparent in the atmosphere. So that's why you can see the through dust, through fog, the SWIR image is quite visible as compared to the visible imager. Okay, so what are the different applications of this near infrared to short wave IR? So one of the important applications, the remote sensing applications, because to monitor the various kind of crop health, disaster management, and this near infrared and short wave IR detectors are very useful for the autonomous vehicles, like LiDAR applications, like detection and ranging applications. This short wave IR detector wavelengths or detectors are very useful. Okay, because you know that the 1.55 micron wavelength range is lasers are eye-safe lasers. So the detectors are very useful to detect this 1.55 micron laser. Okay, because you know the visible lasers are actually very is actually damaging the retina of the eyes, so it's not useful for the actual LiDAR applications. So most of the autonomous vehicle applications and the LiDAR or the face recognition applications, LiDAR, this near infrared or the short wave IR lasers or detectors are used. And one more thing is the divergence angles. If you know, the beam divergence angle is directly proportional to the wavelength. That's why radars are not giving that kind of resolutions in this kind for the LiDAR applications. Okay, so because you know the radar having the wavelength in the range of 200 micron, more than 100 micron, so it has a higher divergence angle. So and the nearby cars I cannot distinguish. So but LiDAR for the lasers and the 1.55 micron wavelength is very narrow, is very wavelength is very low, so divergence angle is very low, and the resolutions point of view is better. So one more application is the fiber optic communications, because you know, as you know, all the fiber optic that communication wavelengths are now used. Hello.
Yes, sir. You may continue.
Okay, so for the fiber optic communications also, the 1.5 micron lasers are used, and that's why the detector is very useful in the fiber optic communications network, and to detect the 1.55 micron lasers. And there is another application, the free space communications. Nowadays, actually, there is actually high demand of the building the networks in the satellite communications using the 1.55 micron lasers, because you know that 1.55 lasers having a high bandwidth, because now we are talking about the terahertz bands frequency as compared to the radar, where we are talking about some gigahertz, let's say 10 to 20 gigahertz. So bandwidth is huge when you are going to when you use the 1.55 micron lasers, and that's why detectors very useful to detect this kind of the near infrared to short infrared lasers. So what are the materials that are important for these detectors? So as I already mentioned, the indium gallium arsenide or indium phosphide, because if I incorporate little bit indium on the gallium arsenide, I can make a ternary compound like indium gallium arsenide, and I can grow on indium phosphide. So I can tune the band gap from 1 to, let's say, 2 micron. So what instrument I use? Because SCL has kind of reactor, like this is a MOCVD reactor, metal organic chemical vapor deposition reactor, where we grow the material like India. This is a typical layer structures which is used for the near infrared to shortwave wire detectors. Okay, so as I already mentioned, this is the indium gallium arsenide, the active layer on they are grown on the indium phosphide substrate. This is basically layer structure. This is basically a photodiode. You can see this is a P-type material. This is a I layer PIN. Okay, this is basically PN diode, and intensity layer is sandwiched between the P plus and N plus, so I can enhance my absorption. Okay, so absorber layer is basically indium gallium arsenide, and a particular composition of indium. Let's say 53% of indium is only lattice matched to the indium phosphide substrate. So there is a so that to ensure the defect-free growth on indium phosphide substrate. For that, we use a gallium arsenide this kind of MOCVD reactor, where we grow this kind of material above 800 degrees centigrade to 1000 degrees centigrade. Okay, and and you can say this how we actually grow a P-type and N-type material. It's basically in situ epitaxially we can incorporate the dopants. Like in silicon, we implant the arsenic, phosphorus, or boron for TP type on a particular region of the silicon. But here, actually, we grow epitaxially the dopant or the N-type and P-type material in situ. Okay, so during the growth itself, we actually create our PN diode in the on top of the either gallium arsenide substrate or indium phosphide substrate. Okay, so after growth, what we do? We mainly do the material characterizations. How good my material is, or what is the quality of this material that is grown on the substrate. Okay, so for that we mainly do the X-ray diffraction measurements. Basically, we have to check that whether there is any kind of lattice mismatch present in the layer or not. So you can see if there is a lattice mismatch, there is a distinct peak between the epitaxial layer and the substrate material. So if it is a perfectly lattice match, there is a single peak on the in the XRD. So and this will confirm you that the layer quality is very good. Okay, so and another is the optical measurements. So this is a basically structural measurement. There is an optical measurement to know the band gap of the material. It provides the band gap of the material. So basically, as I already mentioned, to detect a particular band, I have to know what is the wavelength of wavelength of light it will actually it will detect or it will absorb. For that, this PL is very important. The material characterization tool. Okay, so and apart from that, to see visually, the physically that how the layers are grown on the substrate. So we mainly use the transmission electron microscope or the microscopy to see the layers actually how the quality of the layers grown on the substrate. Okay, so you can see this is a properly indium gallium arsenide is grown on this top of the indium phosphide substrate, and some other type of materials how it is grown. So there is a clear contrast between the images, or the contrast between your transmitted image is giving in the transmission microscopy, and to show you the quality and the different materials that is grown on the indium phosphide substrate. Okay, so after growth, then we're coming to the fabrication part of the material. So after confirming the quality of this material, then we go to the fabrication part. Okay, so we do the mesh etching of the to make the different kind of pixel, because I have to use these detectors as in a form of a imager. So I have to make a 2D area imager. So I have to etch the pixels. And then on the top of that, I make a kind of indium bump. And as you know, that unlike silicon, it doesn't have any kind of readout circuit. So we actually use silicon readout circuit on top of the compound semiconductors, so that after detecting the light or after generating the electron hole pair in the detector material, and that how I'll get the signals, or how I'll detect the signal in terms of current or voltage in the readout circuit. So for that only, I have to sandwich the silicon readout circuit on top of the compound semiconductor pixels through these indium bumps. And after that, we characterize the imager. So this is a typical that indium gallium arsenide that quantum efficiency or that responsivity of the material on the indium phosphide substrate. They actually is quantum efficiency or responsibility starts increasing above 1000 nanometer, and it will decrease up to 1900 nanometer. So it will actually very good. It has very good response from 1 micron to around 2 microns. Okay, so that's this way it's cover from near infrared to the shorter wave range of the electromagnetic spectrum. So okay. So this is about the near to shorter wave range. Now we're coming to the another part of the spectrum, that is called the infrared part of the spectrum, that is from mid-wave IR to the long-wave IR range, that is from 3 micron to the 12 micron, 40 micron of the wavelength. 3 to 5 micron we call it a MWIR, or medium wave infrared range, or 8 to 12 micron we typically call a long wave infrared range. Okay, so detectors very useful in these ranges because it's a lot of applications. Let's say for remote sensing applications, various kind of environmental pollution monitoring applications, like various kind of toxic gases like carbon monoxide, methane, carbon dioxide, nitrous oxide, they have their fingerprints, absorption fingerprints in the infrared ranges. So I can detect this kind of presence of this material or presence of the toxic gases in the environment by measuring the detector's signals. Okay, in these wavelength ranges. Okay, and then defense applications, because most of the this night vision imaging applications in the defense, they use these ranges, mid-wave IR to long-wave IR detectors, and basically especially long-wave IR range for this night vision imaging. Okay, for that only detectors are very useful. For the as you know that long-wave range as our body at room temperature emit LWIR range and its peak emissivity around 10 micron wavelength. Okay, so for any kind of, that's why in night vision imaging, the long wave IR range detectors are very useful for the various kind of industrial applications like power transmission in the lines. Any kind of leakage is there not, like corona discharge is there not, this kind of application. This LWIR detectors are very useful. Various kind of medical applications like skin temperature, any kind of skin temperature detections, or in skin cancer detections, tissues are there or not. It will generate kind of different temperature mapping. So it can be detected using these kind of detectors. And apart from the very kind of deep space astronomy, these detectors are very useful. You can see this is basically that Hubble telescopes the image. Okay, you can see that in the deep space so many cool star information or information missing in the visible imager, because in the so many cosmic dust are present, and various kind of that molecules are present which absorb the visible part of the electromagnetic spectrum, but that infrared range is quite transparent in this dust, so that so many informations I can collect using this kind of LWIR imager. Okay, so what are the materials used in these detectors? So many materials are used. So many materials are used to detect this LWIR and MWIR detector range. But mainly, so like indium antimonide material, it can cover 3 to 5 micron. Mid-wave IR range can cover. There is another popular material is called mercury cadmium telluride material, which can cover 3 to 5 micron and 8 to 12 micron range. There is another very popular material nowadays is called a type 2 superlattice. It can cover 3 to 5 micron and 8 to 12 micron. There is another popular material is called the aluminum gallium arsenide quantum oil infrared photodetector. It can cover 3 to 5 micron as well as 8 to 12 micron. So there is a flexible of materials present in the compound semiconductor this category, or the compound semiconductors to detect the near infrared, short wave IR infrared, then mid wave IR infrared, long wave IR infrared. So many flexibilities there. So I will discuss mainly the quantum Well infrared detector that is based on gallium arsenide material. Okay, so basically this all the MSc and students, they know that there's basically particle in a box problems. Basically, this is one of the very good applications of this particle in a box problems in this detector material. So basically here what we do, we mainly grow different quantum wells like in a particle in a box. Basically there is a quantum well, there's a two different materials like gallium arsenide material and there is aluminum gallium arsenide material. So gallium arsenide material is band gap is lower as compared to the aluminum gallium arsenide. So the gallium arsenide material is actually like a quantum well or the well material, or is a sandwich, or in terms of potential it will actually the energy is lower and is from some quantum wells. Then what will happen, as you know, that if we have a like a kind of quantum well, it will form kind of discrete energy states. Okay, and that discrete energy states actually follow this rule and relation, that is when how it depends on the thickness of the layer of the quantum well is basically inversely proportional to the energy. So basically that if I increase the thickness of the layer, my energy will be lower. So and if I decrease the layer thickness of the layer, I can increase the energy. So I can tune my the energy spacing between the two discrete states. Okay. Now what I will do, how to detect the IR light? Now when I dope this layer, gallium arsenide layer, when I dope, my Fermi level is above this ground state. Then now what will happen? If any IR light fall on the detector, my electrons are already present because my Fermi level is above this ground state, because I have already doped this gallium arsenide layer. So electrons are already present. Electrons are jump from the lower acceleration state to the higher acceleration state. So it will absorb the IR light. And then what will happen? It will coming to the next well. So basically tunneling mechanisms will be there because of the bias I applied on this N plus gallium arsenide. There is a 2 N plus contact layer and the two sides of the quantum wells. So to collect the carriers. Okay. So when there is a charge is generated, I can collect through these two contact links. Okay. Like that way, I can make the that I can detect the IR detector out of gallium arsenide and aluminum gallium arsenide quantum wells. Okay. So this is basically a particle in a box problems. Okay. So now, as I already mentioned, I can tune the wavelength of detection by changing the layer thickness. If I change the layer thickness of the gallium arsenide well, I can tune my absorption or the detection wavelength. Okay, but the issue is that for this kind of quantum infrared photodetector is that it cannot detect the normal incidence light, because this has some polarization selectivity, because this is called inter subband transitions. Because interband transition means from the electrons, if it is formed at the valence band, it will coming to the conduction band. This is called interband. But now in this case, to absorb the IR light, the transition takes place from the in the same conduction band. So it's called a inter subband transition. So inter subband transition is basically very polarization selective. Actually, basically to make it this polarization to detect this IR light, because of the polarization selective, I have to use a gratings. So that what will happen? What grating will do? Grating will diffract the light. Okay, so that I can detect my normal incidence light by diffracting the normal incidence to a diffracted angle, to create the normal incidence to diffracted angle, so that I can detect the light using this inter-subband transition. Okay, so this is basically a basic principle for this quantum Well infrared photodetector. Okay, so now coming to the what we hello. Professor Sundar?
You are audible.
Okay. So actually, basically, what we do, what actually mainly steps we follow actually to fabricate or develop these kind of detectors. Initially we mainly design the detectors. Then we design the layout. Then we design we design the mask, and then we fabricate the mask, and we fabricate the detectors, and then we packaging, and then we testing the detectors. Okay, so this is basically a workflow of our activities. So how we'll design the detectors? We mainly design the detector initially using processor and device simulations. by using a kind of ticket tool, either Silvaco or Centaurus ticket tool, where we can design all the detector dimensions and what are the process parameters needed, means what is the typical doping concentration needed in the p type and n type, how deep we need in the how deep the junction is needed. So all these kind of informations I can collect from using kind of ticket simulations for the device simulations, and as well as the process simulations. Okay. So, and there are two mainly process simulations gives you the doping profile and all the kind of process point of view, like etching profile, diffusion profile, deposition process. This we actually finalize using the process simulation. After the process simulation, then we simulate the device, like for the IV characterization, CV characterization, for the potential profiles, electric field profiles, and optical response, the detector responsivity. So this is basically this tool we use to design the detectors. Okay. Then coming to the next workflow, after the design the detectors, then we design the layout. Means basically the floor planning of the detectors on a mask. Yeah, we call a mask is a chrome mask. Okay. So basically it decides the different kind of process sequences. We use different mask layers for different kind of process sequences. Like one mask is used for the implantation, one mask is used for the etching, one mask is used for there's a contact definitions. So different mask layers is used for the different processes. Okay. After finalizing this mask, we fabricate the mask for the fabrication of the detectors. Then we coming to the fabrication steps. So there are different kind of fabrication steps we use, mainly kind of lithography. I'll not go details in this the process details. So basically we use implantation, lithography to define the different kind of N-type and P-type the layers inside the silicons. Okay, then we etch the pixels. Okay, then we passivate the pixels, or the sidewall passivation would be either using the oxide or nitride. Okay, then we deposit the metals for the contact definitions. Okay, after getting this, we actually complete the fabrication. Then we coming to the dicing part. Okay, so after that we dice this is a complete processed wafer in the basically 18-inch wafer. This is a complete 18-inch wafer. After going to the this packaging divisions, then they actually dice the wafer, and they actually put it on a actually package, and they actually seal the package, the dice from the top side. Then from the all the kind of testing and all the kind of qualification happen for this kind of package detectors, and finally it is actually for the going for the characterization part of the activity. So actually in the characterization activity, we mainly follow the two procedures. One is the wafer level characterizations, and another is the package level characterizations. In wafer level characterization, we mainly use IV and CV measurements. Okay, after processing of the wafer, you can see this is actually this is actually manipulator is there. These are kind of tungsten probes are there. Okay, these are the tungsten probes. You can see here. This is actually probe stations. We actually place our detectors, fabricated detector wafer here. There is a different dice are there before dicing the wafer. Then we probe the dice on the appropriate contact, and we measure the IV and CV profile of these dice. Okay. Okay, so what this IV and CV gives? IV characters gives you dark current and leakage current level of the detectors, breakdown voltage, photocurrent value. Okay, and CV gives you the capacitance voltage, gives you the capacitance of the detectors, full depletion voltage of these detectors, and this kind of information we can actually get from this wafer level measurements using IV and CV measurements. Okay, so after the wafer level measurement, then we use we actually follow the die level measurements. After actually that packaging, we use these dies in a kind of quantum efficiency systems. We use a kind of monochromator, where we can tune the wavelength from let's say starting from 300 nanometer to up to 1100 to 1200 nanometer. We can tune the wavelength of light using a kind of grating spectrometer. and we follow the light on the detectors. You can see in the detectors, a CCD imager is here, linear imager is here inside this and the socket or in the this board for the characterization purpose. Okay, so and different channels or different, actually as I already mentioned, different kind of clock signals are coming from the clock drivers, and we apply the different kind of voltage signals or the clock pulses to the CCDs to actually measure the output of the CCDs in the response of the light. Okay. Also, okay. So after that, we mainly characterize the responsivity and quantum efficiency of the detector. So we mainly follow this kind of calculation or the actually measurement procedure. We actually or the so after if incident the light on the detector, I will get some kind of current out of the detectors, and we know some kind of using some calibrated detector, we know the irradiance value in terms of watt per centimeter square falling on the detectors. And as you know the area of the detectors, from this kind of expressions we know we can estimate what is the responsivity in terms of ampere per watt actually is estimated from the detectors. And if we know the responsivity, we can estimate the quantum efficiency of the detector. So this is a typical quantum efficiency value of a single detector. This is a quantum efficiency value of a CCD image sensors. Okay, and you can see the CCD is quite responsive. Has quite sensitive from starting from 400 nanometer to up to 900 nanometer, even 1000 nanometer also. Okay. Okay, this is actually typically actually for the visible image sensors like CCD, silicon CCDs. For the IR detector image sensor, we mainly use this kind of the measurement setup, where the source is black body. We use a black body source. We use a cryostat because, as you know, that the IR detectors having the materials are very low bandgap material. Bandgaps we are talking about 0.2 EV, where the silicon we're talking about bandgap of 1.12 EV. So it's very low bandgap material. So thermal generation is very high in case of IR detectors or IR detector materials. So that's why we actually use a cryogenic temperatures to detect this material. Basically, these detectors are compound semiconductor IR detectors, mainly actually operated in the cryogenic temperature, like from let's say 77 Kelvin to 150 Kelvin. Okay, so for this measurement, we actually shine the black body source from this kind of filter or chopper, or there's a kind of mechanical shutter or mechanical chopper is used to digitize these continuous signals and falling on the detectors. And okay, placed inside the cryostats, and we use the source meter unit or the current voltage measurements, and we can measure some kind of noise measurements. We also use a kind of gain to amplify the signals, and we ultimately getting the output signals from the detector in the response of the higher incidence light. Okay, so typically, so this is a basically package detector. We okay, so we also use FTIR for this for the spectral response measurements of the IR detector. Okay, and this is basically integrated responsivity. We use the integrated response of the detector, because all the I cannot distinguish. I cannot spectrally selective. I cannot spectrally tune the wavelength using this setup. This basically gives you the photo response of the detector in the response of the black body source. But with the spectral response measurement, we use the FTIR or Fourier transform spectrometer. We use to get the spectral information measurements of the detectors. Okay, so we basically after that we dice the detectors, and we package the detectors in these kind of packages. We use these setups, and we characterize this. We typically use the wavelength ranges from 3 to 14 micron. Spectral resolutions we use typically 0.01 micrometer for the this set of resolutions we use. We use two different detectors like MCT and kind of thermal detectors for the measurements. Okay, we use cryostats for this cooling of the detectors. The temperature regions we use normally we use 80 to 300 Kelvin. Okay. Apart from this optical detectors, we also develop various kind of the charge particle detectors I already mentioned for various kind of high energy physics experiments. Some of the detectors have been already used at CERN, Geneva, to estimate the incoming energy of the particles, to track the particles and the time of arrival of the particles, type of particles falling on the detectors. Okay, this kind of there's these kind of applications we can use these detectors. This is basically we call it 8 cross this is silicon pad detectors. This use very high resistive wafer so that it has very high breakdown voltage, because you can know you can see that what is the detector specifications. You can see that the breakdown voltage is generally needed greater than 500 voltage or 450 voltage. So for that, very high resistive wafer is required. Okay, and operating voltage, you can see this operating voltage is 120 to 160 volt. Okay, so for that also we need a specific resistivity and specific thickness of the detectors. Okay, and the thickness is also important to estimate the energy of the incoming charge particles that is falling on the detectors. Okay, so this is fabricated here at S.A.S. Basically, this is a diced. This is a full 6-inch wafer. Okay, and this is a diced 8x9 pad array coming out from this wafer. Okay, so this is dimension is around around 8 around around 8 centimeter or 9 centimeter. Okay, 10 mm by 10 mm pad size. So die size is 8.2 centimeter cross 9.2 centimeter. Okay, so how we design these things, because as I already mentioned that the breakdown voltage is very critical parameters to meet this kind of detectors. So we use different kind of guard rings to spread the electric fields out from the detector region. This is basically detector regions. We use different kind of guard rings out of this actual detector regions to spread the electric field out in the outward directions, or we take the peak electric field from the actual detector side to the away from the detector side, so that I can increase my breakdown voltage. Okay, so this design we can do, or we design using the TCAD software tool. And this is a kind of measured data. So this is a capacitance voltage measurement. You can see that this capacitance, or the 1/6 from the capacitance, is saturated at around 140 volt. So this is you can see that for this specific wafer of the resistor, wafer of the the detectors, actually the full depletion voltage comes at around 140 volt. Okay, so this is very important parameters, the full depletion voltage to meet. We have to meet to design or to develop these detectors. And this is a kind of the reverse characteristics of the detectors is the IV measurements. You can see the breakdown voltage. These are breakdown characteristics. You can see breakdown voltage starting from 400 nanometer to 700. 400 voltage to 700 volt. So this kind of detectors is very useful for the charge particle detectors for the high energy physics experiments. So with this, I'm concluding my lectures. If you have any queries or any questions, you please feel free to ask.
Thank you, Dr. Das. It was really an enlightening and thought-provoking talk by you.
So it was
this
very
lecture has really provided us with
it was very lengthy lecture.
valuable insights.
Hello.
Hello. Yes, sir.
Yes.
Okay.
Yes, Professor.
Am I audible?
If you have any, yes, if you have any queries or any queries from the audience side, please feel free to ask.
Okay. So I'm directly inviting the audience participants to raise their questions if there is any. Although he has talked about each and every aspect of optics as well as semiconductor electronics. Participants, you may ask questions. Please unmute yourself and introduce yourself before asking the question. The talk is open for queries and questions.
Thank you, sir. Your session was very informative to all of us. Thank you for your informative session. My name is Manvin Singh from Bareilly College, Bareilly, Physics Department. I'm a physics student. Sir,
voice
my
is cutting off. Your voice is not clear.
sorry, sir. Maybe the connection is a bit more interrupted here.
Your is actually no, his voice is actually is cutting, not clear.
Sir, maybe network issue, sir.
बाहर चले जाओ बाहर.
Now it is
हाँ, भाई
audible.
सारे फन पे.
Manvendra.
Yes, sir.
Okay. Now you may ask the question.
Yes.
Sir, there is no question, but there is a query of mine that what are the current research trends in semiconductor photodetectors? Are emerging materials like graphene and perovskites likely to replace the orientation of silicon-based detectors? Sir,
Sorry?
am I audible?
No, last part I cannot hear. Your last sentence I cannot hear. So,
sir, my question is, what are the current research trends in semiconductor photodetectors? Are emerging materials like graphene perovskites likely to replace conventional silicon-based detectors?
see, for the visible part, let me clear. For the visible part, no material cannot replace the silicon because the maturity point of view, because silicon is very highly mature. Okay, so like nowadays, actually, the silicon CMOS image sensors has a huge market for detecting the visible to the near infrared range. Okay, even CCDs are quite used, very popular for the space applications. Okay, CMOS image sensor has a huge market. So silicon cannot be replaced by any kind of that this kind of materials like graphene, and you are talking about some perovskite is not possible because stability point of view, silicon is huge, is a high stable. Okay, and the cost point of view, so and is very low cost, and the size of the area imager, because that any kind of perovskite, and if you're talking about the large area stability or large area growth or large area patterning is very challenging. When you're talking about 1K by 1K pixel area or the 1K by 1K CMOS image sensors or CCD image sensors is a huge area. So, and all the pixels should give you the uniform responsivity, uniform output or the uniform response. So, and so that you will get a very good pictures in the field of view. So if you see all these things and the responsivity value, if you see, it's very difficult to replace the silicon. Definitely silicon will be there. But and what about the current trend in the research in IR detector? Okay, IR detector side, yes, that different type of material like that very popular material, indium gallium arsenide, as I already mentioned, is very difficult to replace. It's very mature material in SWIR range. Although so many other material like 2D materials are there, but maybe 2D material like black phosphorus are there, but it's very difficult to replace because it is just again the stability point of view, long-term stability, and the maturity of the technology. Okay, and for the long wave IR like type 2 superlattice, antimonide based, or the mercury cadmium telluride, as I already mentioned, is very difficult to replace because they have a very already very mature technology. Yes, some materials are there. They are actually, so many researches are going on for some kind of advanced detectors. Okay, but they have their own application, they have their own field, they have their own area of interest, but difficult to replace this kind of workhorse materials like silicon or compound semiconductors.
So Manvendra, I think you have received your answer.
Hello. Yes, sir. Yes,
is there
sir,
any
yes, sir.
query from the participants?
I got my query. Yes, sir. There is a.
Good afternoon, sir.
Yes.
So my name is
Okay.
Aditi Sharma.
Yes.
And I'm a student
please.
of MSc second semester.
Okay.
So my
First of all,
question is, what are the major challenges with it?
First of all, I would like to ask one thing. So for the MSc student, do you have any courses on semiconductor optoelectronic devices or any kind of optoelectronic or semi devices like silicon, compound semiconductor based optoelectronic, lasers, LEDs, detector? Do you have any courses on this?
So we have lasers in a syllabus.
Laser.
Yes, sir, lasers in a syllabus, but
Okay.
of the third semester.
Okay, you please ask your question. Please ask your question.
So what are the major challenges researchers face in developing high-speed and low-noise semiconductor photodetectors?
Major challenges in high speed.
The high-speed,
Major challenge.
low-noise photodetectors.
Auto detector, high speed, low noise. Yeah. So the main thing is that no, the high speed. If you're talking about the high speed, okay. So for the high speed and there is a response or the responsivity, they are not contradictory. Okay. So to get a very high speed means transit time limited. Let's say to get a very high speed, I have to use a very thin detector material. Okay, you understand? Okay, so then what will happen if I use a very thin material to get a very high speed, my response will be very low. Okay, my responsivity will low. So to get very high response in a very thin layer, this is the main challenge. So at the same time, high speed and the high responsivity to get this very easy. This is basically a challenging thing. So people are use various kind of photonic structures on the detector material so that with a very thin layer, how to increase the absorption, how to increase the responsivity, how to increase the quantum efficiency, and with a very thin layer, so that at the same time I can increase the speed as well as the responsivity. This is one of the challenges. Okay, and and the noise point of view. Hello.
Yes, sir.
And the noise point of view, if I increase very thick layer, if I use very thick layer to use to get the very high response, as you know, very thick layer gives you the more number of noise in terms of leakage current. Okay, so your dark current will be more if I use a very thick silicon substrate or thick layer of the silicon or any kind of material. Okay, so these parameters like speed, noise, and responsivity, they are contradictory to each other. Okay, so this is the main challenging thing. How you can design a detector so at the same time you are getting high speed, low noise, and high responsivity. So for that you have to use different materials design or different kind of detector design or different kind of photonic structure design on top of the detectors. So you have to combine photonics and electronics in the same platform to get the speed as well as the high speed and high responsivity. You understand, or or is it clear?
Yes, sir. Thank you, sir.
So with this question, I think we should close the interacting session. And really, it was wonderful talk, very informative, very enlightening. I hope the participants would have enjoyed it, and it will really raise the queries. So many queries will be arising around the participants about these semiconductor detectors. Uh, Really, this talk will open the collaborations as between industry, academics, and research institutions, which are proposed by or expected by our NEP 2020, and this will really bring together education and research institutions very close. We sincerely hope that today's interaction will inspire our students and young researchers to pursue careers in semiconductor science and photonics, microelectronics, as well as advanced materials research. It is my to formally propose the vote of thanks. May I now request Professor Ritu Agrawal, convener of today's program, to kindly propose the formal vote of thanks. Professor Ritu Agrawal.
Hello. It's nice to be here.
Hello, madam.
Can you hear me?
Yes, ma'am.
Thanks, Professor Sundar Singh ji, to give me an opportunity to present a vote of thanks. Respected Principal Sir, esteemed speaker of today's talk, Dr. Sona Das, guests from other faculties of our college, my departmental colleagues, dear students, alumni of this department, and IAPT members who have joined us online on Zoom link. I'm here to present a vote of thanks on behalf of whole department. First of all, we are indebted to Secretary of Managing Committee of Bareilly College and our Principal Sir for their continuous support and encouragement to organize such academic events for the benefit of the students of our department. I express my thankfulness for their continuous motivation and encouragement. Big thanks to Dr. Sona Das. Our department express a high gratitude for the time and efforts by Dr. Sona Das, who has given this valuable and informative and very knowledgeable talk to our students and to us also. It was really a pleasurable evening to have you here with such nice talk. It was really an immense knowledge imbibed in this lecture. We would like to have you here physically also, if you have time and if we can arrange a physical meeting sometime in the future. My sincere thanks are for Dr. Rupinder Singh ji also, who is PRO Semiconductor Lab, who has coordinated this talk. We are very much thankful for his efforts to organize this much awaited talk. My thanks are to Professor B.P. Tyagi ji also. He is National Coordinator IAPT exams, who has continuously joined us in this meeting on the Zoom link. I am thankful to Professor Shubhra Katara, Head of the Department, Statistics Department, and Professor Sangeeta Singh, Head of the Department of Zoology Department from our college, who spared their time to listen to this informative talk, and they really enjoyed the talk. My sincere thanks are for Dr. Jaspal Singh and his team to provide technical support to the talk, to arrange this talk. Although we are sorry, Dr. Sona Das, to have wasted a few minutes of yours in the beginning, because we had organized the talk in the designated conference hall, the smart class, audio-visual seminar room. But the problem of power failure was suddenly, we had met the sudden power failure, and the generator also crashed at the last moment. So we had to shift the venue from there to our department. So in that process, some time was wasted. We really apologize for that delay. Next, my thanks are for all departmental colleagues, especially Professor Sundar Singh, who has made all the efforts to communicate, to coordinate, and to arrange such meaningful talk. He has spared almost a month of his time to coordinate and materialize such talk. And lastly, but not the least, I express my thanks to the students also who took so much interest in attending the class, in attending this lecture. And I'm sure they must have been benefited and they must have enjoyed this meaningful and knowledgeable talk. Thank you. Thanks, Dr. Sona Das again. Thanks, Semiconductor Labs Chandigarh. Thank you for your cooperation, for your time. And we look forward to have many other such events in the future. Thank you.
Thank you, ma'am.
Thank you, ma'am, for your formal vote of thanks. With the permission of our dignitaries, we conclude today's online lecture. Thank you all for your gracious presence and active participation. We look forward to welcoming you again in our future academic programs. Thank you. Have a wonderful day.
Thank you.
With this, I am closing this session. Thank you, everyone.
Thank you.
Thank you.